everyone. Today I will present our topic about Green's theorem. Before discussing the theorem itself, let me briefly introduce its background. The Green's theorem is named after George Green, a self-educated British mathematician. In 1828, he published the main idea of this theorem in an essay related to electricity and magnetism. Although his work was not widely recognized at first, it was later rediscovered and promoted by Lord Kelvin, making Green's contribution well known in the field of mathematics. Green's theorem is one of the fundamental theorems in a vector calculus. It established a relationship between a line integral around a closed curve and a double integral over the region enclosed by that curve. In simpler terms, instead of calculating a line integral directly along the boundary, we can convert it into a double integral over the enclosed region. This transformation often makes many mathematical problems much easier to solve. In this presentation, we will explain the theorem, discuss its condition, and demonstrate how it can be applied through several examples. Slide is about Green's theorem. Simple, but this theorem is a mathematical shortcut. If you look at the equation in the middle, it shows the calculating the path around the outside edge of a shape. The left side is equal to calculating area inside that shape in the right side. But to use the formula, our shape and our math must follow four simple rules. First, it must be closed loop. This means your starting point and ending point must be the exact same spot. Second, it must be a simple curve. This just means the line cannot cross over itself. Think of a circle or a square, not a figure 8. Third is a direction matters. We have to move around the shape in a counterclockwise direction. Imagine you are walking around the line. The inside area must always be on your left side. And finally, the math function P and Q must be continuous. This just means the function are smooth and have no breaks or undefined point anywhere inside the shape. As long as we have a closed, non-crossing shape going counterclockwise with smooth function, we can use Green's theorem. Now, I will explain the condition where this theorem cannot be applied. First, if the curve C is an open curve or an unclosed arch, it does not enclose a region D, so the theorem cannot be used. Second, if the vector field has a discontinuity, it is not differentiable or contains a singularity such as division by zero inside the region, the continuity condition is violated. Therefore, the theorem is not applicable. To conclude, the theorem only works for a closed curve with a continuous and differentiable vector field.
Next, I will explain how to verify Green's theorem for the vector field vector f of x and y, which is given as x squared plus y I plus xyj. The boundary C for this problem is defined by the region between the parabola y equals 9 minus x squared and the line y equals 0. According to Green's theorem, the closed line integral of f dot dr is equal to the double integral of partial q over partial x minus partial p over partial y. From our vector field, we can identify p of x and y x squared plus y and q of x and y as xy. By calculating the partial derivative, we find that partial p over partial y equals 1 and partial q over partial x equals y. These values are then ready to be substituted into the double integral for final verification. To solve this, we evaluate the double integral of y minus 1 dA with limits of x from -3 to 3 and y from 0 to 9 minus x squared. Integrating with respect to y first gives us y squared over 2 minus y. After substituting the limits and simplifying the expansion, we get the integral of 63 over 2 minus 8 squared plus x to the power of 4 over 2 from -3 to 3. Finally, integrating with respect to x yields 63 over 2x minus 8x cubed over 3 plus x to the power of 5 over 10. By substituting the values of 3 and negative 3, we calculate the final result, which is 468 over 5. Next, we use the direct method starting with curve C1, which is the parabola y equals 9 minus x squared. We parameterize the curve by setting x equals to t, y equals to 9 minus t squared, where t range from 3 to negative 3. This gives us the position vector r vector of t and its derivative r prime of t, which is I minus 2tj. Finally, we transform the vector field into terms of t by substituting x and y. This results in f of t becoming the vector 9, 90 minus t cubed, which is now ready to be integrated. Finally, we evaluate the line integrals for both paths to complete the verification. For C1, we calculate the integral from 3 to negative 3 to the dot product ft dot r prime of t dt, which simplifies to the integral 9 minus 18t squared plus 2t to the fourth, which gives a value of 378 over 5. Next, for the straight line C2, we parameterize x equals to t and y equals to 0, given as ft equals to vector t squared comma 0. Integrating t squared dt from negative 3 to 3 results in 18. By assuming both results, the total closed line integral f dot dr is 378 over 5 plus 18, which equals 468 over 5. Since this matches our previous double integral result, Green's theorem is successfully verified.
This is case study 2. We are asked to evaluate the given line integral using Green's theorem. The region is bounded by the parabola x equal to y squared and the vertical line x equal to 4 as illustrated in the graph. In the next slide, I will explain the solution step by step. First, I identify P and Q from the given line integral. Then I apply Green's theorem, which converts the line integral into a double integral. Next, I calculate the partial derivative. The integral becomes 4y squared plus 3 minus x squared. Next, I determine the region bounded by the parabola x equal to y squared and the line x equal to 4. Their intersection give y equal to plus minus 2. Therefore, the limits are negative 2 to 2 for y and y squared to 4 for x. Finally, I substitute these limits into the double integral. Finally, I integrate with respect to x and substitute the upper and lower limits. After simplifying, I integrate with respect to y. The final value of the line integral is negative 736 over 105. This shows how Green's theorem simplifies the calculation by converting a line integral into a double integral. Next, let's see how MAPLE solvers solve this problem.